Right, we've got two identical projectiles, A and B. They've both been launched with the same velocity. A is launched at an angle of 60 degrees, B is launched at an angle of 50 degrees, and we're going to assume there's no air resistance. We want to explain which projectile has a greater kinetic energy, or they could be the same when they're each at the top of their trajectory. So first of all, I'm going to draw a little diagram. A is going up at 60 degrees. And B is going up at 50 degrees, so not quite at as high of an angle. So I thought about this two different ways. First way you can think about it is as a projectile. So if we're talking about at the very, very top, your y velocity goes to 0, but you still have an x velocity at the top, the horizontal velocity. If we were to, let me draw the angle, 60 degrees versus 50 degrees, they're both being shot with the same velocity, so v naught and v naught. But the x component is not the same. The x component for A would be v naught cosine of 60, whereas for B, it'd be v naught cosine of 50. This one is a, like more horizontal angle, so it would have a greater x velocity. So because the only velocity at the top is the x velocity, the one that has a greater x velocity will have the greater velocity at the top, and therefore the more kinetic. So that would be B, has a greater kinetic energy at the top of its trajectory, because it has a greater velocity at the top. And now we need to explain how we know it has a greater velocity at the top. So at the highest point, the vertical velocity is 0, and since the horizontal velocity is constant, the only velocity at the top is the horizontal velocity. So since B is launched with the same velocity, right, with the same v naught, but at a lower angle, that means it has a greater horizontal component of the velocity. So we're saying that because it's launched at a lower angle, it has more of an x velocity. At the top, you have 0 y velocity, only x velocity. So at the top, B is faster, and therefore it has a greater kinetic energy. The other way, so I'm going to say or, the other way you can answer this is about is using energy. So they're both starting with the same kinetic energy, right? They're starting with 1/2 mv naught squared. But because A is shot at a higher angle, it's going to reach a greater height. So because it's going to a greater height at the top, it'll have more potential at its top and therefore less kinetic energy. So the two both start with the same kinetic energy, but because A is shot, actually let's say B is shot with less angle, B is shot at a lower angle, it reaches a lower height, so has less potential energy, which means more kinetic energy at the top compared to A at the top. A, who goes higher, has more potential energy and therefore less kinetic. So both got the same answer, right? Either way, we're saying that B has a greater kinetic energy at the top, B has more kinetic energy at the top. Here we use projectile motion to explain it. Here we use energy, both completely valid. Pick the one. You should understand both, but you don't have to explain it both ways. What would the speed at the top of each projectile be? So at the top of the projectile, right, at the highest point, that's going to be only the x velocity. If you take, here, actually let me draw it off to the side. If this is my v naught and I shoot it off at an angle theta, right, to get the x velocity is just going to be the cosine, right? This is going to be v naught cosine, is your vx. and then your initial y velocity is going to be v naught sine. So that's the opposite side right here. So at the top, it'll only have the x velocity. So A's velocity at the top, is just going to be, top has no e, that's dumb. Is just going to be v naught cosine of A had an angle of 60. And B's velocity at the top is just going to be v naught sine, oh no, not sine, it's still cosine of 50 degrees. And that is because at the top, the vertical velocity is 0, so you only have the horizontal, which is the same as what it was from the beginning, v naught cosine. Which projectile reaches higher? So the one that reaches higher is A because it's shot at a higher angle. So we'll have a greater initial vertical velocity, right? They actually have the same initial velocity, but because they're shot with the same v naught at different angles, their v naught sine theta is going to be different. V naught sine of 60 is greater than v naught sine of 50, so the vi for y is greater for A, which is why it then goes higher. So shot at higher angles, so reaches higher. You could also maybe do kind of like the inverse of this. You know that the x velocity is going to be faster at the top. So because the x velocity is faster, right, we just said this, because x velocity is faster at the top, it has more kinetic energy, which means less potential because they both started with the same. So then B goes not as high, A goes higher. Forces, everybody's favorite. We're going to draw the lengths of the vectors to reflect the relative magnitudes. So this guy's got its force of gravity, I'm going to call it M2G. This one I'm going to call it M1G. They both have tension. This one needs to accelerate up. This guy needs to accelerate down. So we know M2G is bigger than tension, and we know that tension is greater than M1G. And this is the same rope throughout, so it has to be the same tension. So you have to have T on each one the same. So what I'm going to do is I'm going to make T 2 units long, T and T, and then I'm going to have M1G just 1 unit long. That way it accelerates up. And I'm going to have M2G 3 units long. That way this one accelerates down, and the T's are still the same. M2's big, yeah, good. We want to derive the magnitude of the acceleration of block 2. Now it doesn't matter which block we're getting the acceleration for, right? They're connected, so it's going to be the same acceleration. So we're going to just write our net force equation. So F net equals T minus M1G, because it's accelerating up. Here, net force is M2G minus T. Replace F net with MA, specifically M1A and M2A. Now I'm going to add this over to get M1A plus M1G to get tension, and now that I have tension, I can substitute it in. So that's M2A equals M2G minus, make sure you subtract all of it, right? If this is your T term and you're trying to subtract T, you better subtract each of these, so either put it in parentheses or distribute the negative sign when you write it. So I'm going to get rid of the parentheses and distribute now. I'm going to add the M1 over, M1A plus M2A equals M2G minus M1G. To get A by itself, I'm going to factor out the A, that's M1 plus M2. Alrighty. And then just divide that over. So M2G minus M1G all over M1 plus M2. And we should always think, does this make sense? So M2, but going against this guy's weight, right? So these should be subtracting, and then over the total mass, M1 and M2. Now, what would the acceleration be now that there is a third mass? This third mass is just an extra mass in the system. See how it's not helping pull it any faster either direction? It's just more mass to have accelerating. So you should have said this is the smaller acceleration because you're keeping the same force pulling the system, right? You just have more mass to pull. So you have same forces pulling the system, but now have more mass. So that's like A equals F net over M, right? If this stays the same, but this is more, then this would have to be less. So you have less acceleration. Now we're going to actually derive a formula. So this I'm going to call M1G. This is just tension, but this is a different tension because I have two different strings. So I'm going to call this one T1. This one is T2, M2G, and then this guy feels T2 and T1. There's no friction, so we can just leave it like this. So net force here would be M1A is T1 minus M1G. This guy's acceleration, M3A, is T2 minus T1, right? Pulling minus this pull. And M2A is M2G minus T2. So let's get T1 by itself. T1. And I'm going to get T2 by itself. Oh, sorry, add T1 over. I'm going to plug this in here. And substitute that in for T2. Oh dear, this is annoying. Make sure you subtract all of it. And now we need to get all of these A's over here. So we've got M1A plus M2A plus M2A equals M2G minus M1G. When you factor out the A, that's just going to be over M1 plus M2 plus M3. And what you'll notice is it's almost the exact same equation as up here, but now you're dividing by a third mass. So I still have the same force pulling on the system, right? The same like net force on the system, but now over more mass, which will mean less acceleration. So that's why this is consistent with what we just said in part C. Now, if there were friction, what would happen? So you should have said smaller, because friction is always going to decrease the energy, right? It's always going to go against the motion. So you could think about it in terms of energy. I thought about it in terms of force. Force of friction will always oppose motion. So you have more force against the motion, which means a smaller net force, so less acceleration. Ooh, I hate that I gave you so little room to do this. So basically this is the exact same, but now you have a minus friction force. So I'm just going to go back and start rewriting all of these and say this guy, right, these two aren't going to feel the friction, only the guy on the table, which is the M3. So I'm going to say minus force of friction, which would be mu M3G right here. And then that would be adding on to T2, so that's plus mu M3G, which when you plug this in for T2, now you have a minus mu M3G right here. So your equation would be M2G minus M1G minus mu M3G over now to check is this, if this is consistent with what we just said, well, I'm going to be taking away an extra term. So see how you have subtracting force, so you'd be getting a smaller net force, so you'd be getting smaller acceleration. I would not use direct relationship here because you have like not just terms being multiplied and divided, but like added and subtracted. So think about for subtraction, that means take away. The more I take away, the less I have on top, therefore the less acceleration.